Let me just say, energy production and use is a large and still growing domain. The availability and use of energy is dependent on the capacity of the planet to supply many resources and also the capacity of the sinks of the planet to absorb waste products. BP has recognized these linkages and set itself the goal of better understanding them. It set up the Energy Sustainability Challenge programme to understand whether pressures on natural resources might constrain the way the world produces energy. We thought that understanding the science would help clarify what we have to factor in terms of technology and policy solutions as we transition to supplying energy for the 21st century market. Let me just say what this talk's going to cover. A little bit of context around energy futures, a little bit talking about energy consumption and energy sources. I'm going to introduce the links between energy and natural resources, which is just some insights from what we've learned from our experience in running the programme, and in particular running a multi-university collaborative programme. And then I want to just dive into a little bit more detail just to give you some glimpses in a couple of areas on water and minerals. But then I'd really like to move into a discussion and thought might move that discussion towards the role of materials, which I think is the interest of people on this. So thinking about the context in which we're working in the energy system, population and income are the key drivers behind growing demand for energy. And if you look at the chart on the left here of projected increase in population, you'll see the world's population is projected to increase by around 1.5 billion people to reach nearly 8.8 billion people by 2035. And then over the same period, gross domestic product is expected to more than double, with around 1/5 of that coming from population growth and 4/5 from improvement in productivity and productivity per person. We also expect China and India together to account for almost half of that increase in global gross domestic product, and we expect the OECD economies to account for around 1/4 of that. So then when you combine that with looking at what that means in terms of consumption by region, and this is from the BP Energy Outlook. I mean, nobody can predict the future with a crystal ball, but it is a projection. We see that translates into growing energy growth, more industry, more people moving around, and so that's the frame that we have for thinking about this for starters in terms of where demand for energy is going. We also just think a little bit about energy supply. Our analysis has shown that the world has abundant technically accessible resources to meet global energy demand through to 2050. It shows that we estimate the total energy theoretically accessible is around 450 billion tonnes of oil equivalent per year. It's more than 20 times expected annual demand. And one theme I'll come to is what 1 billion tonnes of oil equivalent is just over 40 exajoules. Current use of primary energy was probably around 500, 600 exajoules a year. And I'll keep on coming back to the theme of units because as I think we'll appreciate the people who are on this call, the SI system is a really helpful system, and it's good just to be able to get an idea of the magnitude of the relationships between energy and various other resources, and they're often hidden under obscure units such as. With all due respect to the people from Illinois who are on this, acre-feet of water, which is very helpful, I guess, when you're in the agricultural business, but doesn't help those of us brought up in the SI system. And that's not a dig; it's just an observation that if we can have common units, it really helps. And what we believe is that technology can unlock plentiful supplies of almost all forms of energy, from fossil fuels to sunlight and wind. Several of these resources could theoretically meet all primary demand on their own. However, resources, both fossil and non-fossil, are unequally distributed, and hence one region's best choices will differ from another. The absolute volumes of resource here are less important than other factors such as cost of supply, or the energy density, or remoteness from centres of demand. Also, supply chain constraints and intermittency, which we see with wind and solar in particular. And when taken together, this means only a limited proportion of their full potential will need to be accessed by 2050. And so the question is a bit more like, will we have enough energy, but more of what kind of energy do we want? And so growing demand and plentiful resources from different areas. And if we then think, well, how is that linked to other resources? Energy production and usage is linked to many natural resources. This was the center of our studies in the Energy Sustainability Challenge program. Just thinking about the linkages between energy and the atmosphere, and this diagram with arrows which broadly proportional to the magnitude of linkages. The atmosphere, there are close linkages to the carrying capacity of the atmosphere. Nearly 60% of greenhouse gases are from fossil fuel use, whilst nearly 30% are from agriculture and land use change. And considering links to land, biofuels use around 2% of global crop land. Thinking about materials, approximately 10% of global primary energy is used in the mining and processing of materials. And it's been estimated that around 5% of steel is used in the oil and gas industry. Also, looking at the linkage between water and energy, water is needed for using oil or gas and for oil refining processes to produce fuels, and indeed for most generation of electricity. And now let's try and put these amounts into perspective. Globally, renewable freshwater resources of somewhat over 40,000 cubic kilometres are available each year. And humans withdraw about a tenth of that, it's around 4,000 cubic kilometres. That's 4,000 billion cubic metres, equivalent to around 600 cubic metres per person, as an average across the whole world. Now, obviously, great regional differences. And of that 4,000 billion cubic metres that humanity withdraws, around 2,700 is withdrawn for food, nearly 500 billion cubic metres are withdrawn for energy, and 800 for domestic and industrial use. And most of the fresh water withdrawn for the energy sector is for thermal power generation, for cooling, and most of that is returned to watercourses, albeit at a slightly higher temperature, and some evaporates and is essentially lost from the local catchment area. And this really points to one of the facets of distinguishing between withdrawal and consumption in water use, and the need to get really clear metrics of these things, which was part of the purpose of the project, and trying to get beyond reacting to headlines, but trying to put everything into a numeric, well thought out set of metrics. And oil, gas, and coal production also require water for displacing oil and gas, for fracturing rock to produce gas, or suppressing coal dust. We estimate that somewhat less than 0.5% of global freshwater withdrawals are used for that. The challenge with water is a local issue. Its availability depends on where you are in the world. And so let's just consider a couple of cases relating to BP's main sector, oil and gas. But that's an overall frame for beginning to think about the linkages between energy and natural resources, and also for setting a frame of thinking, are there trade-offs, other ways of optimizing the system? If you use water for one purpose, does that mean that you can't use it for something else? and what's the implication of that. And so that's a basic theme that I'll come back to in this talk and really like to discuss with you, because I think materials are also part of the global system, and it'd be interesting to understand where they fit in that and can fit in enabling energy to be available, not just where we want it, not just produced, but so it's used efficiently. Just thinking about water usage and oil and gas production, and I've got a couple of images, one from North American gas production at the Anadarko area, and then the one on the right is the field in Egypt, the Saqqara development. It's almost always needed for producing oil and gas, and to maximize productivity, water is injected through dedicated wells to displace the oil or gas from the pores of the rock and push the valuable fossil fuel up through production wells. There it's treated and, where possible, recycled or reused. For conventional oil production on land, the average freshwater consumption intensity is estimated as 21 cubic meters per terajoule. Terajoule is about 3/4 of a barrel of oil. If you include offshore production, the world average freshwater intensity is about 15 cubic meters per terajoule. At this stage, let's put these units into perspective. And I guess if I was in a room with everybody here, I'd be interested to get your own perspectives on this, but we can't do that quite here. So 1 terajoule is about the energy content of a road tanker full of gasoline. Global oil production per year is maybe 200 million times that amount, a few hundred exajoules. The solar energy received on the planet every minute is around 6 exajoules. So just worth putting these into perspective. But a declining amount of freshwater use in fossil fuels extraction due to reuse and replacement by lower quality water has been documented in several areas of the world. So generally, where the industry can use a lower quality water, that's the way it's moving to. Natural gas is the most water efficient fossil fuel. Conventional gas freshwater consumption intensity averaging less than a cubic meter per terajoule, compared with the average freshwater conventional oil production of 21 cubic meters per terajoule. Estimates for water consumption in the US shale gas between 3 and 17 cubic meters per terajoule. Less than 0.5% of all human freshwater withdrawals are used to extract fossil fuels and uranium, and that corresponds to about 9 billion cubic meters. So just thinking about water usage in oil refining, and this is taken from our refinery in Whiting, that I guess the people in Illinois know as a near neighbour. Let's think about refining. The process of refining oil to produce diesel or gasoline uses water in significant quantities, withdrawing about 12 times the volume of throughput, and consuming, that is evaporating the atmosphere, about 0.5 cubic meter per cubic meter of oil processed. So a big difference between withdrawal and what's consumed. 12 times withdrawn, half evaporated. And these correspond to around 270 meters cubed per terajoule withdrawn, and 13 cubic meters per terajoule consumed. And maybe I should have said it earlier. I mean, reminder, perhaps people are very clear with their large numbers. Exajoule, 10 to the power of 18 million terajoules. And so, once again, really clear to be about our definitions and units, and be clear to distinguish between withdrawal and consumption. So those are a couple of little insights of water use in the more traditional energy industry, and some of the results of the energy sustainability challenge in digging around to get good data, because what's we're saying is there are lots of reports and there's lots of footprinting that's been going on, but it really needs going back to the source data and getting current data to get a good handle on it. Let me now just talk a little bit about another dimension of natural resources and energy, and that's minerals in electric vehicles. What you've got to picture, electric vehicles and salt lakes. This is an example of how changes in technologies for energy use need to be assessed against physical availability of natural resources. I'm sure that all of us on this call are seeing more and more electric vehicles. Reported that there were just over 565,000 globally in 2015, with an 80% increase over 2014 in Europe. But once again, we need to put this into context. That's out of 70 million cars of all types sold globally in 2015. So, 500,000 out of 70 million, less than 1%. If you look at the International Energy Agency 2-degree scenario, their high electrification 2-degree scenario, 59% of passenger vehicles sold in 2050 would be either full electric vehicles or plug-in hybrid electric vehicles. Let me emphasize this is just a hypothetical scenario, but under that, lithium requirements and cobalt and nickel would increase substantially. Under the most aggressive scenario, in 2050, 88% of currently known reserves of lithium would be depleted. Annual production would be 22 times more than what the world is producing today. Under the 50% recycling case, the cumulative demand would be reduced, just maybe to 67% of currently known reserves. However, this would require recycling 240,000 tons of lithium per year, around 7 times today's production capacity. Now, around half of lithium reserves are booked in Chile, where nature has concentrated the element in lakes, similar to the one shown on the right. I also didn't have a photograph that had permission to use, so this I had to make do with one that came from my camera of a similar lake in the high Andes. So I'm sorry you're getting the camera and slideshow, but well, this is what we have to do. So this is an example of an interesting materials problem. Materials around base elements. What I'll say in this is people often talk about lithium, but you need to consider the others. You need to think about cobalt, given where a large proportion, around 50% of cobalt produced in the Democratic Republic of Congo last year. And so you need to think of where materials come from and what that means for their future development. But generally, more reserves are booked as needed, and people are able to ramp up production. So anyway, an interesting materials problem, but I think that the disciplines of people in this webinar may hold even more solutions as the energy system is transformed in the future. And this is really what I'd like to explore as I begin to move to the discussion phase of this. But let me just talk about the benefit of having a systems approach that ensures clarity of context, so that decisions in any one technical domain can be taken in a way that's optimal for the whole system. Also, the approach of having good scientific discipline on metrics and units ensures relative magnitudes are transparent. We saw the example with water consumption and water withdrawal. And I've mentioned how having consistent units is really helpful. And also, these two aspects enable priorities to be decided on and clarify the motivation for research. It means that we're not just focusing in one narrow area of the energy domain, but we understand how it relates to the global system on which we're part of. We want to understand what are the big problems, what's worth working on. And in the BP-sponsored work under the Energy Sustainability Challenge, we fostered collaboration between research institutes and across disciplines. And in some ways, that's exciting and interesting. I appreciate there's a natural setup with 4 institutions in ICAM. We were running across 16 institutions. You don't get natural collaboration as of right, but we encouraged it, and it came along, and it'd be great to hear about your experiences in how that works, and if there are experiences that we have that we can share. But getting people together and getting them focused on what are interesting big problems is a start. And then thinking about the multidisciplinary approach, I mean, it makes me think, so what role is there for material specialists? Sensors to understand the linkages between these different parts of the systems, membranes for improving desalination, how can we improve efficiencies and minimize waste? Can we lightweight things or get things to the right weight? Where's better insulation possible, better seals? And before we really provoke the discussion around where materials fit in that, let me just sidetrack into a piece of work from our research partners. I should say was done before the BP funding. It's from John Cullen and Julian Allwood at Cambridge, and shows the global energy system and how about 88% of primary energy is lost or degraded and wasted. And looking at this Sankey diagram, where each line, the width of the line is proportional to the amount of the energy, enabling you to trace where the energy goes. The left-hand side shows the primary energy sources with the units in exajoules, so showing oil around 152 exajoules, and you trace that through the grey, showing it mostly goes into engines, but how a lot of that ends up wasted as heat. Only a small blue line comes out from that, which is going into motion. Obviously, you can see that when you trace through the primary energy that's used into electricity, a little bit of the grey line on the left going through into electricity in the centre of the screen, and obviously a lot of gas used in electricity, and then you see a portion of that that's used in electric motors, and then that's quite efficiently converted into motion. There's much less loss. So I put up this as a means of having a frame, and I think that's one of the things I advocate for in this work, is having a global frame, so you can then drill down into what's really important, and start looking at it. Well, what do you really need to do, so that of all that 500 exajoules of primary energy on the left, we can do rather better than getting just useful energy of 55 exajoules out the right-hand side, just the motion, heat, and cooling light and sound, with so much wasted in heat loss and friction, and indeed fuel losses in transit here. I hope my cursor is being seen on the screen. Yes, it is. That's fine. So really, that kind of sets the scene for a discussion, and I would also like to say, well, are there any actual pointers from nature that we might be able to think about? Personal interest of mine, and I'd love to get discussion going on that. And so if you think of pointers from nature, and excuse the pun on that for those who realise that is a pointer, but you just think of what's possible with insulation. I mean, insulation and light weighting they have to be two of the things that would make most difference to the global energy system. I can, you can look at the insulation that's on polar bears. That they have a black skin, but then a sort of translucent fur. I mean, there have to be designs to improve insulation. So I'm hoping to be besieged by good ideas of all the work you're doing on that, and hear about that. I mean, I make the observation of seals. I mean, seals can be very good on dogs. Methane leakage. When people are worrying about methane leakage, something must be right. Lightweighting, pretty slim. Sensors, I think we all know about the capability of sensors. So really, without further ado, as I said, I'll take about half the time. I'd like to move to provoking some discussion amongst yourself as where do you think developments in materials could make a real difference, and what would it take to make it happen,